HEPEC seminar. Our speaker today is Farinaldo Queiroz, and he joins us from University of California, Santa Cruz.
You pronounced correctly.
He commented actually the workshop too. That's good at incorrectly as well. But he'll be talking about the status of the WIMP report.
Thank you for the invitation. It's a pleasure to be here again. Quite cold this time. So, in this talk, I'll give a brief overview of the WIMP miracle. I'll start talking in a very general way about dark matter, so everybody from broad expertise can understand what's going on here. And later, it'll be very specific, okay, towards the end. In case any questions, you just interrupt me anytime. Don't leave it towards the end, okay? Just ask. I don't have many slides, so we just chatting, and then we can ask our questions. Feel free to interrupt. So what's the WIMP miracle? So the idea is that dark matter particles in the early universe were annihilated into standard model particles. But as the universe cooled down, and expanded, those dark matter particles were no longer able to annihilate into dark matter particles, so they froze out. And those left over dark matter particles are the particles that we can observe today. Okay? So in this plot right here, it's just you have the yield. Let's say that's the abundance, okay? It's the abundance of dark matter particles. That's the temperature of the universe. So as the temperature decreases, or as the universe expands, you can see the abundance of dark matter particles decreases. But at some point, the freeze out happens, and then you have some constant leftover abundance of dark matter particles. Okay? The weaker they interact, the more abundant the dark matter particles we have today. If they interact strongly, so you have fewer left dark matter particles. Okay? That's everything so far. Well, I like to always talk about dark matter in a not so boring way. And the idea of these status of the WIMP miracle can be explained in few slides in this cartoon right here. So how does that come about? So in we have TAMU, which is a long-standing result that requires some modulation that is consistent with the dark matter interpretation. It's not saying that's dark matter, but it's consistent with WIMPs carrying off the crystals of sodium iodine. And we have cognac was in early 2010, roughly. They also observed in that time some excess events that could be explained by dark matter particles. And then people like my former supervisor, Dan Hooper, and Neil Weiner, whoever you like most, they were claiming, woohoo, we discovered dark matter. However, shortly after, Xenon 100 came and said, no, those events you guys are seeing are not dark matter. So those guys right here started claiming, well, there are some scintillation efficiency issues in the xenon detector that might remedy this whole picture, actually make the WIMPs, the region of Fermi space that dark matter particles can explain the access, is still viable. It's not ruled out by the Xenon 100. And to make a very long story short, we have now CDMS, silicon events. We have lugs. I put AMS on the other side. Someone might ask me that later, why I was biased to choose that side of the road. If I'm telling you that this side over here is the dark matter interpretation, and this side over here is saying that's not dark matter. And after those signals, those no results from lux, xenon 100, CDMS light, and so on and so forth. So those guys, the dark matter guys, were walking towards the non-dark matter interpretation, like saying, okay, I give up. It's not dark matter then. And there were people still claiming that there were ways around it, how you could still have dark matter particles that could explain those signals without being ruled out by current measurements, such as Jerry Drava, who is a detector guy at Stanford. He claimed that if you have few GV wings, like 1 GV one, you could explain the Dharma signal scattering off sodium only for some weird reason. I don't know. He just said, let's assume for now that we just interact with sodium. I have 1 GV wing scatter just with sodium. I don't care about iodine. Just for now. He said, okay, we can get a cross-section that might explain Dharma, and because it's 1 GV WIMP, at that time would be below the energy threshold with direct detection experiments. We didn't have the CDMS-like results at that time. Okay? But, and then 1 week after, Stefan Perfume and I, what we did was, okay, let's check how reasonable that assumption is. He was right. If from some weird, crazy assumption that we just interact only scatter off sodium, you can explain the Dharma signal. But he's wrong when he says that he's not ruled out by current constraints. Yes, you are. Okay, and we show that he's ruled out by force signal. But I won't get into the details of that. And after this whole picture, we have the Hooperon, right? The Hooperon is just, Hooper keeps putting out papers regarding the galactic axis, and so people call it Hooperon. And we were crazy enough that we wrote a paper with the Hooperon title. I think that was the first time in the literature someone was crazy enough to do that, where we show that what kind of effective operators someone can come up with and still explain the galactic axis not being ruled out by LHC, whatever, direct detection, whatever you can think of. We had this breaking news very recently, which was, I think it was April, I think, this year. Hooper found the dark matter axis. That's a breaking news, which is the gamma ray axis that I was talking about, but this time was just focused on dark matter related to quarks. Okay? That was the breaking news of the year. I'll talk a little bit more about this galactic axis so we can have an overall idea of what's going on in this WIMP miracle regime. So what's the Hooperon all about? We using Fermi-led data, okay, which is a NASA satellite. They found some axis in the galaxy, gamma ray axis towards the 1 GV-ish energy window, 1 GV, 3 GV energy window. And here he shows what's the spectrum of this axis looks like right here for a given gamma. What's the gamma is? The NFW profile, dark matter profile. There is a gamma dependency there. If a gamma is equal 1, means it's just vanilla NFW profile. If its gamma is greater than 1, you're saying just that the dark matter halo profile is steeper than you previously thought. So he's just saying that you need a steeper dark matter profile towards the galactic center, which is sort of what we expected. Okay? And then, given that spectrum, I can use 50. You can use, not micromegas. You can use serialiscope and then compute the gamma ray spectrum coming out of some dark matter annihilation. So what that is you just fix. It's very easy. It's a mathematical one of those, the shift enter codes in Mathematica, where you compute the gamma ray coming from dark matter annihilation, just fix the mass and annihilation cross section, giving a particular finite state, That's it. That's all you need. 3 things. Then you compute the gamma ray spectrum. So if I give you this spectrum right here, you can compute what is the best fit region that reproduces this spectrum in terms of the annihilation cross section and the mass. Okay? That's all they did. And they found in this paper, which was confirmed by several different groups, that dark matter hypothesis is real. Nobody can doubt that. That dark matter hypothesis can explain the excess. Okay? Nobody in this room or anywhere in the world will say otherwise. It can fit the data well. And in this paper, they show the chi-squared, not the chi-squared per degrees of freedom. They just show the total chi-squared. I don't know why. And they said, okay, in our analysis, we find that the chi-squared, the data, has a bias towards dark matter annihilating to quarks instead of leptons. Okay? Because they say the chi-squared is poor to leptons when dark matter relates to leptons. However, one could ask, is this a real signal? Is just an application of Friedman's theorem? Or any competent theoretician can fit any given theory data to any given set of facts? Okay? Before going to that, so, well, but you guys live along theories, so you know that that's a very true principle, right? Hi, you.
I remember about that these parameters can be extended to the fiber wall.
The what?
A theory of these set parameters can be extended to the fiber wall.
So before going to the discussion to whether or not this is a real signal, just like to point out what's the particle physics interpretation of this signal. Okay? So in that Hooperon paper, this is effective Hooperon paper right here, we showed what kind of channels one should have to explain the galactic axis, and maybe not being excluded by other searches. Okay? Those are like pseudoscalar mediators. You can have those mixing between vector axial and vector mediators. You can have also scalar. These guys are fermions, are the dark matter particles. So you can have fermions with pseudoscalar mediators, and you can have scalars with pseudoscalar mediators or just gluon interactions. Just a bunch. I don't expect anybody to remember what was D2, D6, C2, C6. I don't care. Okay? Everybody has to have one take-home message, which is I'm going to give an overview of the WIMP miracle. You might remember the ideas of what I'm talking about. I'm pretty happy with that. Okay? I don't expect you to remember what was the region of the prime space, what explained the whole problem. No, you don't need to remember that. You just look into the paper. Okay? Just the idea. So focus on the idea of the problem. And 90 papers have been written so far on this. So theorists are very good at that. And also Hooper put out a paper shortly after us where he outlined what kind of simplified dark matter models someone could come up with and still be consistent with other searches. At first order, we agree with each other, okay? Why I say first order? Because we use effective operators and they use simplified Lagrangians. So we don't have a mediator, they have. So the LHC bounds, they'll be different, and that's what you expect.
How do they define the model number?
Which number?
Model number, 1, 2, 3, not 1, 2, 3.
No, it's because it belongs to the same mediator. Spin 0, 0, and it's a fermion. So you just change the nature of the fermion. So that's one. For instance, like this one. Direct fermion, direct fermion, and sp1, sp1. That's why it's. And then he called it, I don't know why he. Okay, wait. Why do you call it 2, 3, 4? I'm trying to recall it. 3, 4, 5. Well, they I don't know why he called it. There, I know there. I remember that there are 8.
Probably the
8.
interactions are different. One is gamma mu, the other one is axial motion.
Yeah, might be.
Okay.
But the most important thing is that there are 8 class of models that can currently 8 class of models that you can come up with and explain the Hooper-on axis. That's the take-home message regarding this Hooper-on axis in terms of from a particle physics perspective. And many of them you won't see in the foreseeable future any constraints. For instance, LHC reach, maybe, yes. And then direct detection, never, no, never, yes, no, yes. So few cases then they are probable. You can probe them at LHC or direct detection experiments. Huh? It's no. They say no. Yeah, the powers. That's right. It's Q4, so forget it. Yeah, these powers of the momentum exchange. So. And just a reminder is that in those galactic center simplified dark matter models, you can always derive gamma rays constraints using the galactic center data that Dan and I think I might be wrong. I think it was the first time in the literature that someone showed the constraints beam by beam using the Fermi data. So it's very easy. Well, I'm more a particle physicist than an astrophysicist. So when we were working on this, I said we should derive astrophysics bounds for particle physicists. So we should get this whole quantity because this is the particle physics quantity in the flux, right? The other one is astrophysics. So astrophysics, no, I'm more particle physics. So let's just bound the particle physics quantity so everybody can just come up with a model and then compute that thing and compare with the total flux we found and then derive bounds in their annihilation cross section for a given any annihilation channel you can think of. So now the Hooper-on from that should be astrophysics perspective, not particle physics perspective. When was it? March this year, Joseph Silk and collaborators, Marco Cirelli also had a paper in this topic where they showed that if we include inverse company scattering, actually the previous claim from the Hooper and collaborators that saying that the annihilation to leptons provide a very poor fit is no longer true. However, there is no paper written in that topic. It seems that if dark matter truly annihilates into tau leptons, let's say, or leptons in the final state, they seem to be excluded by AMSO2. But we had a long discussion in the afternoon talking about this with Yuga, Bhaskar, and everybody, that you might remedy that. So you can come up with different background models to change that assumption. Maybe with the vanilla background models, if you have a dark matter particle that annihilates into tau leptons, and you want to explain the galactic center axis, you ruled out by AMS. That's what it seems. Okay? We need a more quantitative answer to that. And that would be the hadrons versus leptons. So it seems, for now, that hadrons seems to be the right answer. Okay? Not the right answer in the terms that they provide a better fit, but it seems that the ones that provide a fit, it still survives the current data. And what about cosmic ray models, gas distribution, magnetic fields, and so on and so forth? It was a paper from, did I put it here? I didn't. Oh, I didn't. So sorry if someone is seeing this. Vinegar, Ilias, and Calore put out a paper where they tried to account for the systematics in the galactic center and see if we change some gas models like cosmic ray distribution, magnetic fields, the galactic center axis in the Fermi data is still there. and they found it is. So even if they come up with different gas models, so it doesn't seem to be a mismodeling of something so far. So they found this. They found, yeah, wait, we changed these wide. We had different assumptions, wide, different models, and everything, and we still find the excess in the Fermi data. So it seems to be a very compelling result so far. So one could ask, okay, besides dark matter, what could explain this excess? We had the pulsars interpretation. Stefano, my current supervisor, he's claiming that maybe pulsars can be, or even pulsars can't explain the excess. Maybe we have some astrophysical processes going on that we don't know about. So it's too soon to claim that that's dark matter there. But everybody agrees that the excess is there. So you can't doubt that so far. So the reason why it should be dark matter, not pulsars, is because the excess extends up to 10 degrees of the center of the galaxy. The axis is very centered around Sagittarius A, and using the pulsars observed by Fermilab today, using the pulsars, they have some luminosity function. Using extrapolating, let's say that the pulsars we know today, let's say we have some of them around the glass center, using the same properties. Let's say I have them. I didn't observe them, I'm just saying, assume they are, that I haven't seen so far. Well, how many pulsars we would need to explain the excess? 2,000. So you would need 2,000 millisecond pulsars to explain the galaxy excess. That's what Dan is doing. However, there was very recent, one question we raised with Stefano was, is the galaxy center really not ruled out for forming dwarfs? Well, they are ruled out. The galaxy center axis is actually ruled out by Fermi dwarfs if, and only if, there are intermediate massive black holes in dwarf galaxies. Okay? That's 1406, so it was in June of this year, where what we did was we took Fermi dwarfs 2014 data, not PAS-8, that was previous PAS-8. So we took their data, and what we did was, let's include the intermediate massive black hole in there, and see what happens with the constraints. Okay? So the current constraints are like this. Let me pick one line. So can everybody see this line right here? Yeah. Yes. Okay. So the current constraints are like this curve right here, something like this. However, if you see that you include intermediate massive black holes in dwarf galaxies, those constraints, they shift by orders of magnitude, many orders of magnitude. I would like to emphasize that I'm not advocating the presence of black holes in dwarf galaxies. I'm just saying if they are black holes, that will happen. Okay? That's what's going to happen if there are black holes there. Why did I come up with this great assumption out of thin air? No. There are some 3 independent observations that what they took they measured the velocity dispersion of the stars of some dwarf galaxies, and they said, well, if we include black holes with masses up to whatever, was 10 to 3, 10 to 4 solar masses, we can still match the data reasonably well. So there is no bias towards no black holes, and there is no bias towards, yeah, there are black holes. So the data doesn't care. Okay? Given that fact, you'll say, okay, if it doesn't care, it gives also can describe the velocity dispersion of the stars. Let's see what happens regarding the dark matter output. So that's what happens. So the constraints get much stronger, and this blue region right here is a region that explains the Hooperon. So the Hooperon, this is just the individual constraints. We performed also likelihood analysis to get the joint one. which is also ruled out. I think I showed that in the next slide. And we also exclude the whole Brown region, which is this one. Okay. So this is the Fermi. This is the black one. This is the current Fermi one, which did not exclude. That was prior to pass 8. Okay. So we have, this is the Fermi one, the black one. So we said, okay, now we have an FW. I don't remember if we showed here the mass of the black hole. Yes. For instance, this dashed dotted one, mass of the black hole. Mass, did we show? Yeah, it's 550, 100 solar. Yeah, 50 solar masses. So 100 solar mass, 10 to 2. For instance, this dashed one, which is right here. So if we insert a black hole of 10 to 2 solar masses, that's what happened to the constraints. That's the Fermi, black. That's ours, dashed. This is the Hooper region, right here. So it's excluded by roughly a factor of 8.
So if you have intermediate mass black holes, you have enough GeV increasing flux that explains that gives you a
Yeah, because what we're simply doing is this. So the flux is proportional to sigma V over m squared, mass of the dark matter squared, m chi, times a J factor. So let's say this J factor is equal 1 in the vanilla case. Okay, just normalize it to 1. When you include a black hole, this J factor increases. Why? Well, it does not necessarily increase. It depends on how the black hole was formed. In our case, we made the assumption that it was increasing, and we have several papers that support that idea, that if we insert a black hole in one galaxy, the J factor increases. But we can discuss much more detail that. Let's say black hole, the J factor increases, okay? This thing is measured, okay? This is fixed. So if this is fixed, this increases by, let's say, 1 or 2 orders of magnitude. I have to change that thing. For a given fixed dark matter mass, I have to decrease sigma V to get the same measured phi. So your constraints get stronger in the sense that because you need lower sigma V, that's exactly what's happening.
Actually,
Very-
I heard this paper, not confused.
Okay.
J is actually measured.
Yeah, J is
So
measured.
you can't just willy-nilly increase it.
Yeah, but I can increase that with, for instance, the velocity dispersion of the galaxy. That's the measured thing.
Yeah, but the J is derived from that.
It's derived from that.
So how are you just arbitrarily increasing this?
Yeah, I can increase, for instance, this thing, I have some error bars in that thing, right? Let's say this is measured. And this is not measured quantity. The velocity dispersion is a measured quantity.
No.
So from the velocity dispersion, and then you say vanilla and FW, I compute that thing, and then I compare with this, I get sigma V over M.
I mean, well, the flux, the uncertainty of the flux you get comes from the measurements and the uncertainties on the J's.
That's right.
That's propagated through. So you can't just say, I want to increase the J to just as much as I want.
That's right, as long as it's within the square root of phi. It has to be within the error bars. But remember, because I have a genericity, this function, I have no idea what that is.
Yeah.
And this thing, you have some input on this thing, but I have no idea what that is. And this has to be equal to the error bars that I have in my flux. So I can, within the error bar of this, I can do this thing. I cannot just like increase randomly. But this thing, I can do whatever the hell I want.
Yeah, I agree. But J, you can't increase J arbitrarily either from.
No, not arbitrarily. You have to change. That's why, for instance, the galaxy we were talking about was 10 to 7 solar masses.
Yeah.
And the black hole masses were like 10 to 2, 10 to 3. That was like 100. So you're not messing up with the velocity dispersion of the stars.
Is the profile getting much steeper in the center, or is that what's happening?
Yeah, it's steeper.
Okay.
get the steeper. If it's steeper, then you get, if you were not steeper,
So I think that's the way I.
and there is also a crucial assumption is that, for instance, I was saying, we can discuss that in more detail because the J factor does not necessarily increase when you put a black hole in there, because it depends on how the black hole was formed. Okay, and there are some astrophysical things, and I know a little bit about it. I'm not an astrophysicist, but there are some caveats to that. So we had that assumption. We had the intermediate massive black holes because the data was not claiming there was no black holes, or the other way around. So I say, okay, if there were black holes, what happens to the dark matter? And then the big assumption comes. Which assumption is that? Saying that this J factor increases. If the J factor increases, and then this thing goes down. And in order to determine what's the mass of the black holes in which one of those dwarf galaxies, we use 3 different methods to say to one very extreme in the sense that was predicting very massive black holes, and one that's very, very mild, saying that the mass of the black hole is really low. And the same question again, is the Hooper excluded by dwarf galaxies? No, there are not black holes in dwarf galaxies. And we had a steeper dark matter profile. Why I'm saying this? Because I took this from Fermi Symposium, okay? Fermi Symposium, those are the current favorite vision to explain the galactic center axis. Cross-section, relation cross-section in terms of the mass. Right here. The only difference because this one has a steeper profile, because the dark matter density assumed to be 0.4. This one was 0.3. So in this region right here, for instance, the Hooper region, the official Hooper region is the red one. So it would be excluded by current Fermi-led path 8, which is this blue curve. If you go to a steeper profile, and then you can escape Fermi dwarf limits. So you need a steeper profile, which is fine because that's exactly what many groups have found, that the gamma, this NFW profile that has gamma equal 1 when it's vanilla NFW profile, that gamma should be greater than 1 to fit the data. So that's sort of what we previously expected. And that's the indirect detection of limpets, because we have Hooper. So I wasted some time to figure out which one of those guys were born, where we were born. And there is a space available, so you can put on your plot right here. Why I'm saying this? Because look at this plot. Do they necessarily agree with each other? More or less, right? They don't exactly match a favorite region. So don't ask me why. So there is some space available for the dark matter lengths. And we got also again regarding this galactic center axis, there is what we should do to determine whether or not we have some dark matter access there. That's the astrophysical point of view. Well, there are systematics that Vinegar already started working on that. Gas model, data-driven background models, and there's one working team that is currently being done in collaboration with Stefan Profum in Finland and Eric Carson. And this paper was pretty good. I think it was the first paper that someone did a comprehensive systematic analysis of the galactic center. And we are working more towards that. But mostly focus on data-driven background models, okay? And now, let's say, okay, given this whole mass you heard down, CDMS, silicon, galactic center axis, how is the WIMP miracle regarding simplified dark matter models? Not focus on the galactic center, okay? Just given current direct and indirect detection constraints and collider. We have there are so many. Bhaskar, if you talk to him in 5 minutes, he'll come up with 10 different simplified dark matter models. One of them, let's say, is Z prime. The Z prime, what means is that just Z prime is the mediator between the dark sector and the visible sector. Every time you hear someone saying Higgs portal, so Higgs is the mediator between the dark sector and the visible sector. Z prime portal, the same thing. Bhaskar portal, Bhaskar is the mediator between the dark sector and the visible sector. Okay? And there are many different setups. You can make the couplings different, crazy. You can do what the hell you want with them, as long as it's consistent with current data. There are setups, for instance, where the Z prime is leptophilic, where the Z primes only interacts with leptons for some reason. Okay? You can come up with particles that is smaller that does that. So let's try to do it in a model independent way. I'm not saying what gauge symmetry I have. I'm not saying what kind of extension of the certain model I have. I'm just saying that we have a dark matter and we have a Z prime interacts only with leptons. That's all I say. Okay? So when Bhaskar come up with a model that Z prime is leptophilic, he can just use those lines. Okay? That's the idea. That's why everybody, if you see in the literature, there were, I think today, 4 simplified dark matter models. Yesterday 6, and then that goes on and on and on. Just like to point out, there is one public code for computing the mu magnetic moment that Will Shepard and I wrote in early this year, which is also again one of those shifty enter programs in Mathematica. Okay, it's very straightforward. Leptophobic, that's the next slide. So I'll be very brief about that. And there is a general case which will appear soon on our archive with Dan and Stefano. Let me just go to this slide. So the idea is, whatever you can think of, you have a given dark matter model. What you want to do is compare with current data, direct, indirect detection, and collider. So what you do is, the easy thing regarding simplified dark matter models, you don't have too many free parameters, okay? Compared to SUSY, for instance. If you look at this indirect detection, where dark matter related to dark matter particles, you have some coupling here that I don't know what that is, and some coupling here. So I have 2 couplings that will determine how strongly the dark matter particle interacts with the external matter particles. Okay? And those couplings are present here and here. So I have 2 couplings. Okay? That's it. And of course the masses of the particles. But couplings, I have those 2. And then I can derive all the signals and plot limits regarding those couplings. Okay? Combine all of them. So that's what we did in this paper. I would like to just call attention to something that people don't usually talk about, which is a misconception, the Z prime portal, not in the Z prime portal, but in a very general way. So people usually talk about dark matter, that's the way I particularly don't like, is in terms of spin-dependent and speed-dependent interactions. However, this is quite misleading. Why? Because there are some interactions that people often call spin-independent, but they truly are not. Look at this, for instance, this. Just one thing, everybody knows what spin-dependent is. The tricky question. Don't think that's that easy. What spin-independent and speed-dependent means? Okay, I'll take you as a bait. What is spin-independent means?
Spin-independent means like it doesn't depend on the spin of the dark matter.
Of the dark matter? Everybody agrees with that? Of the nucleus. Yeah, it's not as easy as you think. You're so used to say spin-dependent, but you don't usually think spin-dependent of what? Dark matter spin or the nucleus spin? Nucleus. That's okay. Now you won't forget it anymore in your whole life. So, for this operator, when you have vector and vector interactions, so we have, this is a the amplitude, okay? So you have vector, vector, you don't have any spin right here, you just have some constant. So this is called spin dependent, fine, and then it's truly spin independent. Let's say this one. This one is known, which is this one right here, O2, O2. It's often called spin independent. We go here, spin independent. We have the spin of the dark matter particle, and we have the spin of the nucleus. But it's called spin independent. Why the hell people call it spin dependent if you have a dependence on the momentum or on the dependence on the spin of the nucleus? Because there's a momentum dependence right here. So what programs such as micromegas does is they take the limit where the momentum exchange goes to 0. So this thing goes to 0, you have just dependence on the spin of the dark matter, which is called spin dark matter independent. It's spin dependent because it does not depend on the spin of the nucleus, not dark matter. Okay? So it's called spin dependent. But this is only true in the 0 exchange momentum limit. Okay? So this is a misconception in this sense. This does not, all particle physics models do not obey this at all. Okay? There are many particle physics models where the exchange momentum is not 0. So you don't have a spin dependent independent definition like classification. You have to say, well, in the 0 momentum transfer limit. Because this table, people are used to take it from micromegas. That's exactly what they have. Spin dependent for each one of the operators. But if you read in detail, I think they have the footnote or something. You're taking the 0 momentum transfer limit throughout the paper. So I'll jump a little bit these monojet and dijet because I can explain in few slides. So what monojet and dijet means. Doing monojet and dijet calculations is kind of boring. You spend lots of time in MATLAB and doing that whole thing. And at the end of the day, you come with plots, and 1, 2 plots is, wow, after all this trouble, I can have with 1, 2 plots. And seems to be complicated to understand. However, you understand what monojet and dijet works like 1 or 2 plots. So you see from now on in the literature, people talking about monojet and dijet bounds, very fancy, complicated plots, but everything can be understood in 2 plots. That's it. Okay? It's just fancier ways to present results. But the physics behind it is all the same. They are all the same. Why? You see right here. So let's look at this one. You have PP producing Z prime, and you have some quarks towards the end. Okay? So you have one jet, dijet. Okay. So the Z prime, in this case, the Z prime is leptophobic. What that means is the Z prime will only couples to quarks. That's why I have only quarks in the defined state. I'm not considering leptons. Okay? So I just have Z prime and quarks. Well, if you look at this figure is the branch ratio of the Z prime into quarks as a function of their coupling. Which coupling is this? This is a typo. This coupling is what GX is. GX, I'll put right here. G chi is the coupling between chi bar, chi, and the Z prime. Okay? So the larger the G chi is, the stronger the dark matter particle couples to the Z prime. So okay, let's fix one coupling. G chi equal 1. We go here, G chi equal 1. The branch ratio is between 6 and 7. For dark matter mass of 10 GeV. When you go to 20, it's almost the same. When you go to 40, it changes a little bit. For Z prime mass of 100, for Z prime mass of 500 GeV, if you have one coupling equal whatever value, let's say I'm choosing equal 1, I'm changing the dark matter mass, which are those different curves dark matter mass from 10 to 300, the branch ratio of the Z prime to quarks is changing by 10%. What I'm trying to say? I'm trying to say is, given one coupling, okay? Given one coupling, whatever that is. If I change the dark matter mass, the branch ratio of the Z prime to quarks does not change much. What kind of signal I'm interested in here? Is quark-quark, which is dijet. So if I change the dark matter mass, I don't care much about this. The signal remains basically the same. Okay? I'm giving a very brief overview of what's going on, but everybody can understand this. There are way more details to that, but the overall picture can be understood in just this plot. So if I'm looking to this kind of signal, dijet, if I change the dark matter mass, I don't care. Those solid horizontal lines are the dijet production cross-section. Look at the dark matter mass. It goes from 0 to 1,000 something. Does the production dijet cross-section change much? No. Why? Just look here. That might be a fancier plot, but I can look just branch ratio. Branch ratio is something that undergrad computes. Right? So the physics is very simple. And something similar can apply for the monojet, but the monojet bound, which is kind of this signal right here, where you have dark matter, you have some EC energy and a jet coming out of here. Now I do care about how the Z prime couples to dark matter. So I do care about the mass of the dark matter, because the mass of the dark matter will determine the EC energy I have. So I do care about the mass of dark matter when it comes to monojet. So monojet, you have those curves right here, those dashed lines. They are very different for kinematics reasons. The production cross-section of monojet when it changes the dark matter mass. Okay? So let me show this plot right here. This one we just show what's those horizontal spiky curves are the collider bounds, and these are the dijet bounds, and this one right here, the dashed one, is the monojet bound. And you can see that there is a quite important complementarity between monojet and dijet, and they are sensitive to larger couplings when it comes to monojet, and not so sensitive when it comes to dijet. For instance, dijet are very sensitive. For instance, look at this. They are sensitive to small couplings, and there is a reason for that. This has to do also, you can just look at the branch ratios and you understand why the dijets are sensitive to small couplings, whereas the monojets are not. And what I'm assuming here, that the Z prime couples just like the Z, just like it. I was lazy that they took from PDG the Lagrangian from the Z and the Z prime. It's okay, let's use the same Lagrangian to see what happens. That's what we got. Okay? The same couplings, couples just like the Z. And then you say, but why did you choose that, Farinaldo? Well, I choose for one simple reason. I know how the Z couples in the standard model. So what happens if I depart from that assumption? Let's say that the Z prime now couples, 50%, I chose random, 50% suppressed compared to the Z ones. If I came here and told to everyone, hey, the coupling is 0.7, I don't know what that is, 0.7, I have no idea what that means. But if I tell you that the one particle couples, right, 50% suppressed to the Z, you have a more physical meaning because you know how the Z couples. So I'm telling you now that for instance, this case, the Z prime couples 50% compared to the Z. So let's compare the cases. Z prime equal to the Z, those are the constraints. When I go to 50% suppressed, that's what happens. The collider bounds go away. The dijets, mostly. Z prime equal to the Z, and Z prime 50% suppressed couplings. And we did this for different WIMP masses. This one for the 8 GeV, for 130, 500, and so on. But the take-home message of this Z prime portal, again, I'm just focused on the I want you guys just to be focused on the take-home message. Don't remember what's the mass range, which is not ruled out. You just look at the paper. That's fine. You can ask me later, send me an email, call me if you want. The take-home message is, if you have a simplified Z prime dark matter model, if you combine the direct detection, indirect detection, collider constraints, look at those curves. The black lines in each one of those curves sets the region of the parameter space which reproduces the right abundance. Okay? So if you want a dark matter model that gives you the right abundance, you have to lie in that black curve. If you see right here, this is excluded right there. That's okay a little bit, and this one is also okay a little bit. Dark matter mass 500 GeV, but the only thing we can see in common in all of them is that when you sitting at the resonance, then you can have a viable, simplified Z prime model that obeys the current constraints. This one is okay just at the resonance. This one is okay just at the resonance. And we did for several dark matter masses. Okay, 15, 1,000, 2,000. We also did for 50% suppressed couplings, 90% suppressed couplings, and so on and so forth. Just showing a few slides. So take home message: Z prime portal. You have to be at the resonance to be consistent with data. Okay, as simple as that. And what about the Higgs boson? The Higgs boson is everybody talks about it. So I'll skip a few slides and talk about the most important thing, which is this point. Everything comes down to this point. Let's say we have Higgs boson. Again, Higgs boson is just, the Higgs is the mediator between the dark sector and the visible sector. And this lambda is just saying how strongly the dark matter particles couples to the Higgs. Okay? That's it. That's what this lambda is. And this is the dark matter mass. This is a scalar in this case. This is the visible width of the Higgs bound. It's just saying that the branch ratio of the Higgs into invisible particles have to be around 15%-ish, 20%, something like that. Depends on which data set you use. And if you, this green region is this green curve is the determines the regional parameter space which reproduce the right abundance. So if you want a dark matter model that explains the right abundance, you have to be in that curve. Okay? And you look right here. Those are the current lux constraints, and those are the projected xenon 1 ton. So the lux already excludes almost everything. So you have a dark matter mass that have to be like around larger than a couple 100 or so GeV. Otherwise, you have to be at the resonance. So you need a very not heavy. I wouldn't call it heavy, but over 100 GeV dark matter mass to be consistent with current data. And if you take into account xenon 1 ton constraints, they'll be very surprised if they observe some signals, dark matter signals. So it may be 2017, I guess, is xenon 1 ton. So in 2 years or so from now, we will see that on the whole below 1 TeV Higgs boson is excluded. You have to be at the resonance. One thing that I'd like to emphasize that is not in this plot and is not probably nobody's talks in these slides is that we are talking about simplified dark matter models. You have to keep that in mind all the time. Why? I showed you this region of the parameter space which gives you the right abundance, okay? Given any particle physics model you can think of, even Bhaskar won't come up with one that does not contradicts with what I'm going to talk about. You have a dark matter model that gives you the right abundance. You can extend that model to suppress that abundance. But you won't come up with a model that will enhance that one. Unless you have, in a given model, WIMP miracle, you have that model and you want to enhance that model. It will be very hard. I just know one case that will do that, but I won't tell. You have just one specific regime where you can enhance that abundance. Otherwise, you will just suppress. Why? Space phase. If you include more particles which your dark matter particle can relate into, you just decrease the abundance. Okay? So what that means is, I can discard right here if I have, but for now this is a singlet scalar model. If I have doublets, if I have triplets, singlet plus doublet plus whatever, plus Bhaskar working on it, you can shift that thing down. You can shift that curve down. You won't shift up, you won't shift down. Why? You will decrease the abundance. What that means is, when you shift that down, you can shift it down by much so that you're not totally excluded by xenon 1 time. For not specifically about this singlet Higgs boson. Any particle physics model, if you extend more particles, put more particles into your model, make it more complicated, you won't enhance the abundance. You will decrease the abundance because you have just a space phase integral. Okay? So you will just suppress your abundance. If you're interested in that, awesome. If you're trying to increase your abundance, if you are in a simplified dark matter model and your particle is underabundant, you're doomed. Because you won't enhance it. Okay? So it's a simplified dark matter model. You're just saying, is excluded? Yeah, excluded, but this in this very specific regime, one singlet scalar period. Just final remarks that we need to be at the resonance, whether it's the Higgs boson or the Z prime boson or Bhaskar boson. Okay? And there are lots of interesting things going on in direct detection. Direct detection now became boring from my perspective. But there are still things going on. I was very fortunate to decide to work on dark matter a few years ago because there are lots of things going on, lots of direct detection. We moved from theory-driven field to now to be data-driven field. That's very good because physics is data. That's all that is. And there is some I put as footnote because it deserves to be just a footnote, which is very recently there was a 2.4, 2.6 sigma, depending on which channel you're talking about right here. The CMS coloration observed some excess events in the EEJJ and UEJJ that would be consistent, it's not an evidence, consistent with 550, 650 GeV leptoquarks. So what we did in this paper with Coover, former postdoc here, and Strumia, was how to account for these access 2 point something. So, okay, you already know. 2 point something is like, it's worth working on it as a theorist, but it's not something that you rate, it's not a red flag. And we just showed there are some really nice connection between leptoquarks and dark matter that can account for the data. Okay? It's really nice. So leptoquarks in this scenario, to explain the CMS axis, I haven't seen nobody like coming up with a very different way to explain this. I've seen some people talking about WRs. I'm not sure if they're so plausible. It's debatable. Anyways, leptoquarks can be tied to dark matter and explain this CMS axis. That's quite nice. I'd like to see them because they're observing two different channels. And my conclusions are, we have all those massy signals. Are these all chasing embodies? Maybe, maybe not. But regardless of that, it's very important for us to keep working on dark matter complementarity to put the WIMP miracle to the test in the next decade. I think most of the dark matter physicists would agree that if we don't see any WIMP signal by the end of this decade, lots of people will start shifting to different, not fields, but different dark matter candidates. Maybe actions will become the most popular dark matter fields in 7 years from now. Probably I would, if I had to bet my house on it, I would bet on that. But that's it. Thank you.
Questions? Comments?
Yeah, I have one question, comment on Z prime product. And suppose you emphasize digit, but if you see the digit bump, without any other channel, you can't tell this is dark matter or not.
What's that again? Sorry.
Okay. If you focus on digit, then if you see the bump, then this doesn't mean this is a dark matter scenario.
If you see any collider signal, I'll be more general than that.
Yeah, but
it doesn't mean that's dark matter. It just means that you have a stable enough particle in your detector.
So what I meant was it's not moving to the dark matter scenario.
Yeah, in this case was because the according to CMS data, the branch ratio could not be equal 1 into visible particles, so it has to be smaller than 1. Josh and
You're talking Z prime, right?
huh?
You're talking Z prime.
No, I was talking. I thought you were referring to the leptoparts case.
No,
you were saying the digest and the Z prime.
Z prime product, then you focus on different parameter space. You say digest is more feasible compared to image.
Yeah.
If that case, suppose I see some digest bump.
Okay.
Unless you come up with other channel, say consistent with that scenario, I can't tell anything.
That's right.
What happened. That's correct.
Yeah, I agree. I totally agree with that. Yeah, the collider things. So people usually who don't work on astrophysics, they badmouth the indirect detection signals because we can't believe in indirect detection signals. But as far as dark matter is concerned, I really doubt that someone will be convinced by a collider signal regarding dark matter. Because how are you going to claim that's dark matter? You can just claim that's stable enough in your detector. If you see a direct detection signal, I'll say, done, we're done. Well, if it's consistent with other signals and so on, we have to double check with other experiments and so on and so forth. But if you have direct detection signal, for me, in my opinion, is the most compelling way to observe dark matter. Indirect detection signal, you can always come up with background model, that is this and so that. Collider, maybe how you're going to claim is dark matter. You're just saying that the lifetime is longer than field cycles. So you cannot claim that you have a dark matter particle was produced in the detector. It just escaped your detector. How is that? It's very different from being dark matter and being stable enough for collider purposes. But the complementarity is still good because if you see something with very good similar properties in detectors or indirect detection, that's already very robust signal, despite the fact that you can come up with background models in direct detection and come up with different models that address the collider signal. But if two totally different approaches have one signal that are totally consistent with each other, that's a very robust signal. That's why people are so eager to see some bump in these Hooper region somewhere else. Because if we see dwarfs, it's Nobel Prize. It's Nobel Prize. If we see dwarfs, Nobel Prize. We won't, I don't know. Probably we won't see them.
Any other questions? Okay, let's thank our speaker again.